Hey there everyone, Mr. D here, and this is going to wrap up our first and second derivative test conversation that we've been doing this week. So for this video, I'm basically going to walk through two examples that already have the work written out, and then we're going to create a graph from scratch based on some clues that are given to us. Just as a reminder, we do have a quiz coming up. You can use a calculator if you think you'll need one, but you cannot have a graphing calculator. So I want to make sure you know how to find these maxes and mins by hand. Graphing calculators do that work for you. So if you've got a scientific calculator, great. Aside from that, we're good to go. All right. So first, number 3 here. We have x to the fourth plus 4x cubed. Just looking at this function, I can see that it is a quartic and it's positive, so I'm expecting something that looks kind of like that. I have no idea how deep these valleys or how high that peak is, but this is kind of what I'm anticipating. So anywhere up to 1, 2, 3 max and mins, and maybe 1, 2 inflection points. We'll see. So first, let's find the first derivative. Straight power rule here. So 4x cubed, 12x squared. Then we want to find when does that derivative equal 0? When does it not exist? Well, this is just a polynomial, right? There's no weird radicals. There's no x's in the denominator, none of that. So it's never going to not exist. It always exists. So that means we don't have to worry about the does not exist part, but we do have to worry about the set equal to 0 portion. So if I set this equal to 0, I need to solve this out. Well, to solve it, I'd factor out a GCF of 4x squared. That gives me x equals 0, and then x plus 3 would give me x equals negative 3. So no, at 0 and at negative 3 is when we could potentially have maxes or mins showing up. So then I need to go through and do my first derivative test and say, okay, values that are less than 0, or sorry, in this case less than negative 3, do those result in a positive or negative derivative value? Numbers that are between negative 3 and 0, does that result in a positive or negative derivative value? Numbers that are greater than 0, what's happening there? So we're taking values and we're doing a sign analysis on our derivative function. Now, when we do that, I notice right here we switch from negative slope to positive slope, which tells me that right at negative 3 I should see a minimum. And then at 0 we're positive and then we stay positive. So visually what that looks like is that I have a positive slope, a brief slope of 0, and then I continue to be positive yet again. So that's what that would look like right here at that moment. All right. So we make our claim. We know it's increasing and decreasing on the given intervals because our derivative is positive or it is negative. And then to find the extreme values, we would plug in our minimum, so negative 3, into the original function. So the original function being x to the fourth plus 4x cubed. Notice we didn't plug in 0 for x because we didn't switch from positive to negative slope. That wouldn't result in a max or min. Sure, it might be a critical point, maybe it's an inflection point, but it's not going to be a max or a min here. So now let's get to our second derivative. We know the first derivative, 4x cubed plus 12x squared. We can get the second derivative very quickly and easily, again, just from power rule. So 12x squared plus 24x, set that equal to 0, and solve. I've got a GCF of 12x, so I get x equals 0 and x equals 2. These are my two potential inflection points. Well, just like we did before with the first derivative, we're now going to do the same thing with the second derivative, where I'm going to do a sign analysis, where I plug in values that are less than negative 2 for this function, between negative 2 and 0 into this function, and something that is bigger than 0, I'll plug that into this function here. And what that does is it tells me the concavity. So we're starting off concave up, and then we switch to concave down, and then we go back to concave up. And from the very start of this, that kind of makes sense, because this was the function guess, right? The function shape that I had guessed. And if we look at it, yeah, it goes concave up, switches to concave down, and then goes back to concave up. So it's really not a surprise there that we're seeing that. We could write out our intervals using the justification that the second derivative is either positive or negative, greater than or zero or less than 0. And to get the specific inflection points, we'd plug in -2, and we'd plug in 0 into our original function. So we'd plug those into the original f of x function to get the y values. So now that we have all of our specifics, we know the minimum value, we know the inflection points, we have enough to make our graph. So I'd take that general shape and kind of fit it to these points that we have needed here. One thing to notice with the inflection point is anytime you have an inflection point here, typically what that means is on either side of it, your slope is going to be doing the same thing. So here's an inflection point. My slope beforehand is positive, slope afterwards is still positive. Here's an inflection point. My slope beforehand is positive, slope after is still positive. So anytime we stay continuing to increase, but have a brief moment where our first derivative would be 0, that's typically indicative of having an inflection point. All right, let's see another one. Here we just had a quick goof on the plus and minus. So make sure that that's reflected in your homework. We take the first derivative, set it equal to 0. Again, the first derivative is going to be a polynomial, so you'll never have a does not exist on that. Solve for x, we get our two values of 2 and -1. So that's going to be potential for maxes and mins. Now this function is a positive cubed, so we just found the x values for that max and min there. We can then find the second derivative. This is going to help us find the inflection point. So the second derivative, set that equal to 0. We get x equals 1/2. So what I've just found are max and min x values. So this would be -1 something, and then this would be 2 something. And then we found the inflection point. And that's 1/2 something. All right. Well, now that we know where our graph is, or sorry, our derivative is switching from positive to negative or equaling 0, we can go through and do our sign analysis. Our sign analysis will tell us positive slope, negative slope. Anytime we switch from positive to negative, we know that there is a max. Anytime we switch from a negative slope to a positive slope, we know that there is a min happening. So we can get our local max and local mins using these x values and plugging them back into the original function to get the corresponding y values. Second derivative, same concept. We know there's an inflection point at 1/2, so I want to figure out what's going on beforehand, what's going on after. So the inflection point happens at 1/2. We are concave down prior to that and then concave up after. So that is this little pattern right here. To get the specific y value for the inflection point, we would just plug in 1/2 for our x value. All right, now let's sketch a graph from scratch. All right, we're given this bit of info. I'm going to go through and make a little first derivative and second derivative number line, kind of like we had before, just to have some consistency and help me visualize some things. So let me make a first derivative line, and I'll use red, second derivative. Okay. So it says we're increasing from -∞ to -1, and then -1 to +3. So that's going to be a first derivative. So -1 and +3 things are happening. So we're increasing, which means it is a positive slope in those regions. We are decreasing from 3 to infinity, So that tells me right here this is probably going to be a maximum value if we switch from positive to negative slope. All right, concave up from -1 to +1. We are concave up from -1 to +1. That's going to be my second derivative. So it's going to be concave up between those two. It is concave down from -infinity to -1. And then again from 1 to infinity. We have an extreme value, a maximum of 7. Oh, it's an absolute max. Okay. An absolute max at 3, 7. Then we have inflection points at -1, 3, so we already knew it was going to be -1. And then 1, 5, and we already knew that was going to be a +1 as the x value there. Okay. So here's what I'm thinking our graph is going to look like roughly. Noticing just off of the concavity, I kind of want to say it looks like almost a downward shaped W, but that doesn't necessarily hold true if I'm talking about, right here at -1, our slope continues to increase. So what if I kind of change that to be something like this, where it continues to increase there? We'd have that little moment where our derivative is 0. Yeah, I think that ought to do it. Okay. So let's get the specific values plotted here. 3, 7 would be right about here. That's going to be my max. Absolute max. My inflection point at -1, 3. I'm going to just call that I. And then 1, 5. Again, calling that I. All right, so let's see if I can kind of get a shape kind of like this to go through these values here. I'll try to color code with concavity as best as I can. So we're going to be increasing. And then here's an inflection point. We're still increasing, but now its concavity is switched. Oops, I forgot to change colors. So right here we're concave down, now we're concave up. And then we're going to end on concave down yet again. Let's just double check to make sure that satisfies all criteria here. We're increasing from -infinity to -1, and then again from -1 to +3. All right, we're decreasing from 3 to infinity, yes. Concave up in this little stretch, good. Concave down here, and then from 1 to infinity, we have our maximum value. I'd say we got it. Nailed it. All right, so that is what that graph might look like. That's it for this video. You know the drill. If you have any questions, let me know. As always, folks, good luck, have fun, be safe, roll tide.